see this paper as being part of a four-step process to improving our assessment of ZEC. The first is to identify the Earth system processes that drive this uncertainty, and that's what we've tried to do in our 26 levers. The second is to estimate their impact on different timescales. The third is then to try and reduce this uncertainty through targeted research. And of course, the ultimate aim is to build models that can better give us an assessment of the zero emissions commitment.
Good morning, good afternoon, and good evening, everyone, and a very warm welcome to everyone joining us today for this Frontiers Forum deep dive session. Allow me to introduce myself. My name is Gilbert de Gregorio, and I'm Head of Partnerships at the Frontiers Planet Prize, and I'm absolutely delighted to be your host and moderating today's session that explores global warming after achieving net zero CO2. So today's deep dive session will be focusing on this lead article entitled The Zero Emissions Commitment and Climate Stabilization, which was published last year on November the 14th, and it's already been featured in both Bloomberg and The New Scientist. Right off the bat from COP28, I guess we can all agree that this is a very timely and topical theme that we're very interested in learning more about. So in their Frontiers in Science lead article and its hub of complementary content, which I invite everyone here to read to explore, the authors Palazzo Corner et al. Present the first comprehensive analysis of Earth processes that control global temperatures and our knowledge gaps for each. Plus, and very interestingly, they introduce a pioneering new framework for building climate models that are better equipped to predict the expected additional change in global temperature once we reach and achieve net zero CO2 emissions. This approach is absolutely crucial for effective climate policies, as also discussed in the complementary publications that you can find in this hub. So the article itself acts as a centerpiece for a lot of great material, including this editorial by Professor Michael Mann from the University of Pennsylvania, a scientific viewpoint article by Professor Damon Matthews of Concordia University, and a policy outlook by Brooke Dambacher and Tessa Khan of Uplift, who we'll hear from later today. There's also a lay explainer, infographics, a video, and also an article that's been published in Frontiers and Young Minds, which is our journal for kids. And during this deep dive session, you will hear from many of the different contributors to this article hub, and you'll also have the chance to connect and ask your questions to them. So what have we got to look forward to together today? So this is today's agenda. We'll kick off with Professor Martin Siegert, who will set the scene for today's discussions. Sofia Palazzo Corner, lead author of the article, will be presenting on whether global warming will stop when we reach net zero CO2 emissions, and will examine what determines the temperature changes once we reach this threshold. The speakers will then come together in a panel discussion, who will also be joined by Professor Joeri Rogelj from Imperial College, Ben Sanderson from the Center for International Climate Research, Dr. Charlie Koven from Lawrence Berkeley National Lab, and Tessa Khan, founder and executive director of Uplift. We'll then open the floor to questions from all of you. And finally, we'll then close off with Professor Joeri Rogelj, who will be delivering some closing remarks. So our first speaker is one of the co-leaders of the Frontiers in Science lead article, Professor Martin Siegert from the University of Exeter. A few words about Martin. He is also the field chief editor for Frontiers in Environmental Science, a globally renowned glaciologist who leads the UK's participation in ground-based airborne geophysical programs, which have so far explored and charted the subglacial environment across 40% of Antarctica. He's also published more than 250 scientific articles in leading international journals, previous co-director of the Grantham Institute of Climate at Imperial College, and Martin is now the Deputy Vice-Chancellor of the University of Exeter, where he's also responsible for supporting the 2030 targets for net zero greenhouse gas emissions at both the university and the county in which he resides. So Martin, with that, a warm welcome and over to you.
Well, thank you very much, Gilbert, for that kind introduction. Just like with all scientific papers, each of the authors involved will have their own story about its origin. And I'd like to tell you about mine. Mine involves an early morning cup of coffee with Joanna Haigh, Joanna and I were co-directors of the Grantham Institute at Imperial some time ago. And without going into too much details about that conversation, it's quite clear we had very different ideas about what happens to the climate and the environment of our planet after net zero emissions is established, or the zero emissions commitment. And that conversation was interesting. We suspected many other people would have similar misconceptions about it from a variety of different perspectives as well. So sometime later, with the help of Joeri Rogelj, which we'll hear from later, we configured a group of specialists from all around the world to discuss and debate the zero emissions commitment. Brilliantly led, I should say, by Sofia, who we'll hear from shortly to take us through the paper. We set ourselves about 2 or 3 months to form a consensus on this. Actually, it was probably more like 2 years, I think, of many discussions and drafts and working things through. But I think we've put together a comprehensive guide to the zero emissions commitment, and we hope it's going to be informative, useful, and interesting. So to tell us more about it, I'm going to hand over to Sofia, who's going to explain everything that we did.
A huge warm welcome, Sofia. Sofia is a climate science and climate policy PhD student at the Centre for Environmental Policy at Imperial. Her research focuses on Earth system extremes with the aim of fully representing the spectrum of possible temperature changes that could occur by the 2100. And a very interesting background, if I may, an accolade of achievement. So Sofia has a professional background in management consulting at the Boston Consulting Group, energy and environmental research at Chatham House, and quantitative risk analysis at Funding Circle. So Sofia, a warm welcome to you. The floor is yours.
Thank you, Gilbert. Thank you, Martin, and thank you to everyone joining us online today. So I'm going to introduce this paper that we published with a question which is probably the same question that brought you here today and was certainly the motivation for our study. That question is, will global warming stop when we reach net zero CO2 emissions? So what do we mean by this question? What do we mean when we say, will global warming stop? Well, historically, and of course still today, global surface temperatures are rising in response to anthropogenic CO2 emissions. We've burnt some carbon, we've got some warming. And so the question is, once we stop burning that carbon, do we also stop our warming? Does no carbon dioxide being added to the atmosphere mean no more warming? And another way to phrase that is, how much additional warming are we committed to after we achieve and maintain net zero emissions? What is the zero emissions commitment? So there are 3 things that can happen after net zero to global surface temperatures. The first is that temperatures stabilize, and the global warming that we reach at the point that net zero is achieved is the same that we have going forwards. There's no change. The second is that we could have some warming, some additional temperature rise after net zero, in which case that global surface temperature will go up a little. Or alternatively, some cooling, and global surface temperatures would reduce. The zero emissions commitment is then a number, and it's a number that quantifies that change in the global surface temperature between the point when net zero is achieved and some point in the future. And zero emissions commitment, or ZEC, as we will abbreviate it, can be 0, meaning no change in temperature stabilized. It could be positive, indicating that there's some additional warming, or it could be negative, indicating cooling. And so the next question is, what is it that happens to the Earth system exactly after net zero, and how does this affect temperature? So if we sketch out what's happening to emissions at net zero, so historically and still today, anthropogenic CO2 emissions are increasing. If globally we stop emitting CO2 into the atmosphere, there are 2 things that we expect to happen. First is that atmospheric CO2 concentrations, which have been rising alongside rising anthropogenic CO2 emissions, are expected to start declining. And that's because CO2 in the atmosphere is expected to be redistributed to carbon sinks in the land and the ocean via the natural carbon cycle. Now this, on its own, would be a cooling effect, but it isn't the only thing that's happening. At the same time, we're expecting ocean heat uptake, which has also been increasing as emissions have been increasing, to start reducing after net zero. And this would mean that more heat remains in the atmosphere, and on its own, this would be a warming effect. And so the question then is, what happens overall to global warming? Is there a balance between this cooling and this heating effect or not? And so we can imagine it kind of on a scale. On one side, we have heating due to this slowdown in ocean heat uptake, and on the other side, cooling due to our continued strong land and ocean carbon sinks. Now, if our slowdown of ocean heat uptake is perhaps a little more rapid than we anticipate, or our land and ocean carbon sinks less strong than we expect, then this might result in some more heating after net zero. On the other hand, our land and ocean carbon sinks remain strong, or if our heat uptake reduces less rapidly than we're expecting, then we might get some cooling after net zero. But it's important to bear in mind that we care both about the magnitude of these effects and also the rate at which they change, because they need to cancel each other out, not only at the beginning, but going forward. So if we go back to this picture that illustrates the question that brought us here, that balance is represented in this uncertainty range that we see on the right-hand side after the point of net zero. If we have the balance tip one way, we might expect a little more cooling, and if we see the balance tip the other way, then perhaps some warming. Now, our best estimate at the moment is that there is no further temperature change after net zero, that remarkably, this balance is struck and continues to be over time. However, these assessments do come with an important and quite substantial uncertainty range. And so that's the second thing that we decided to look at in this paper. And what we're trying to understand is what these processes are that underlie these two macro effects at the top, the heating and the cooling. What are these processes determine temperature change after net zero? And so what we did is we took our quite large group of co-authors who are experts in different parts of the climate system, and we tasked them with trying to build a catalogue of all of the different processes that could affect global temperature after net zero. And this is what we came up with. 26 levers of global temperature change after net zero. We kind of accidentally built our own A to Z. And so these processes are organized into 4 subcategories. We've got land carbon processes, ocean carbon, ocean heat, and physical feedback. Now, these two on the left, land carbon and ocean carbon, they are processes that affect and determine and are determined by the natural carbon cycle. We've then got the kind of physics of the ocean and how heat is transferred between the different ocean layers and also exchange with the atmosphere. And then we have feedback processes which affect and are affected by a number of those other 3 categories and also other parts of the climate system. So this is already a great resource for anyone hoping to study the zero emissions commitment and reduce our uncertainty in it. But of course, ultimately, what we're trying to do is quantify the effect of each of these processes. And so that was the next step we took. The way that we did this is we gave a case study, or you might call it a scenario. And we asked our group of experts to consider a world where global warming was capped at 2 degrees at the point where we reach net zero. So at the point where we reach net zero, there's been 2 degrees of global warming. And we asked how much would each of these 26 processes move that global surface temperature up or down as a percentage of that initial warming. And that's what we're looking at here. So this figure has a few things going on. So let me just talk you through it. On our x-axis, we've got those 26 different levers, the A to Z. And on our y-axis, we have the change as a percentage of that initial 2 degrees of warming. And our two levels there are 1% and 10%, and then some of those are stretching beyond 10%. The colours are indicating the groups, the subcategories. So if we look on our key on the left, we've got land carbon, ocean heating feedbacks, and then the tone or the opacity of those bars is an indication of the confidence that our experts had in those assessments. And so this first panel here is showing the potential impact of each of these processes for global temperature change 50 years after net zero is achieved, so ZEC 50. We then extended that same assessment, but for 100 years after net zero, then further for 1,000 years after net zero. Now, the first thing I should say, which is tempting, is that we can't just add all of these bars up together and come up with a number. Unfortunately, it's very much not as simple as that. But there are two things that we can definitely take away from this figure. The first is the number of processes where we see an impact of plus or minus 10% and sometimes even more. And that is not an insignificant change. The second is the proportion of these bars where the assessment we can make is still only speculative. And that's a real indication of the uncertainty that we still have in a lot of the processes that affect the zero emissions commitment. So if we come back to that illustration of the question that brought us here, our results are certainly not disagreeing that our current assessment contains some significant uncertainty. But perhaps what we're adding to this is that the uncertainty reported in our models at the moment is perhaps not telling the full story. And there might be processes that are not yet included that could either stretch that uncertainty range wider or move it to one side or the other. And why is that important? Well, of course, if we assess that there is a plausible chance of significant additional global warming after net zero, that very much changes the implication of what it means to burn carbon today. So, of course, our ultimate aim is to reduce this uncertainty. But to give you a bit of a flavour of how complex that can be, we can plot it on a kind of simplified version of what the Earth system looks like. Just taking a handful of the processes that we have, we can already see how many interconnections we get. So just starting with the atmospheric processes here, and bearing in mind that the connections that are dotted are indicating processes that are uncertain in our current models. If we add on here the physics of the ocean, we're already seeing, even in this very simplified version, connections between atmospheric feedbacks and, for example, the Passon effect, which is the pattern of surface warming on the ocean. Adding in biogeochemical processes links the ocean and the land. And then we have land processes, which are affected by things like land use and wildfire. So we see this paper as being part of a four-step process to improving our assessment of ZEC. The first is to identify the Earth system processes that drive this uncertainty, and that's what we've tried to do in our 26 levers. The second is to estimate their impact on different timescales, and that's what we've been doing with those bars that you saw across the 3 different timeframes. The third is then to try and reduce this uncertainty through targeted research, and there's more details on that in the paper, but we've listed out quite a long and detailed table with suggested research questions and modelling exercises. And of course, the ultimate aim is to build models that can better or with a narrower uncertainty range, give us an assessment of the zero emissions commitment. So why is it important? What do we gain from knowing more about the zero emissions commitment? Well, perhaps one of the most important things to take away is that if the zero emissions commitment is positive, if we can expect additional warming after net zero, that changes our assessment of how much warming we can expect from burning 1 unit of carbon today. And if we want to stay below particular temperature thresholds, then the budget we have left to do that may be smaller than we think. On the other hand, if the zero emissions commitment is negative, then we may be able to achieve more ambitious targets with the same action, which would be fantastic. And so we've been talking a lot here about temperature stabilization, but unfortunately, a world that has stable temperature or global warming that stops at net zero is not necessarily a world that has a stable climate. In fact, we know a number of things that are guaranteed to continue changing. For example, sea level rise in response to the warming that we've already caused, disruption to ecosystems due to changes in weather, wildfires, droughts, the melting of glaciers and ice sheets, also in response to the warming that we've already caused, ocean warming, which will disrupt the life that depends on the temperature there, and the same again for ocean acidification. So if we were going to conclude with a couple of messages from this paper, they'd really be that the risk of additional warming after net zero is just another reason for us to reduce our initial disturbance to the Earth system as much as possible. And the second is that a world that has stable climate, a world where global warming stops after net zero, unfortunately is not equivalent to a world with a stable climate. And climate targets for both mitigation and adaptation need to take these two things into account. And with that, I'm going to hand over to the rest of our panel.
Thank you very much, Sophia. It's great having that in the future. I can only imagine the level of complexity it was to get all the data, 26 levers, and understanding the uncertainty and interactions between them as well. So thank you for sharing that in a way that we can all identify. So what I'd like to do now is to explore some of the issues that you raised there, and also have some input from Martin and the Frontiers in Science article in a panel session that will be moderated by Martin himself. And a quick introduction to all of those who are joining the panel. We have Professor Joeri Rogelj, who is the current director of research at Grantham Institute, who leads research, training, and innovation towards effective action on climate change and the environment. So Joeri's work connects Earth system sciences to the study of societal change and policy. And his work on climate change scenarios has informed international climate policy over the past decade, and he has a long-serving lead author on the annual emissions gap reports by UNEP, and also on the IPCC reports. He was also a participant on the Transformational Science panel discussion at COP28, which was hosted by Frontiers. Next up, we have Ben Sanderson, who is a climate scientist and research director of the Climate Mitigation Group in Oslo, Norway. And his work looks at how to better characterize the uncertainties of mitigation technology and negative emissions, alongside the development of formal statistical tools to highlight the conditional risks of mitigation decisions. We have Dr. Charlie Koven, who is a staff scientist at Lawrence Berkeley National Lab, whose research focuses on the relationship between climate change and the Earth's carbon cycle, looking specifically at high latitude feedbacks. And he was also a lead author on AR6, the sixth assessment report of the IPCC. And last but very much not least, I'd love to welcome Tessa Khan, who is an international climate change and human rights lawyer who has spent decades supporting grassroots, regional and international movements for justice, serving as an expert advisor to UN human rights groups and national governments. She's also the co-founder and executive director of Uplift, which resources, connects, and elevates ideas for a just transition away from fossil fuel production. And to end this introduction with an impressive fact piece, in 2019, Tessa was named by Time magazine as one of the 15 leading women in the fight against climate change. A huge warm welcome, everyone, and I'd love to now pass this over to our moderator, Martin.
Thank you, Gilbert, and well done, Sophia, for that really very well put together presentation about the paper. First question is going to go to Joeri. Hi, Joeri. And it's this: considering the policy and technological landscape, what are the most critical interventions or actions that can be taken to optimize our chances of achieving, maintaining a stable climate after we reach net zero?
Yeah, thanks. And also my thanks to Sofia for a great introduction. If we look at the implications of what we have learned from this exercise, and what this exercise has been further supporting and corroborated, is that there are key milestones that we need to take into account, and that also international climate policy as such needs to take into account. And net zero, or achieving net zero emissions, is one of those key milestones. This research has not changed that in the slightest. What this research also shows is that there is some uncertainty about what happens thereafter. That uncertainty can fall in our favor, and that's really good. Then we would be very happy. But from a risk management perspective, which policy basically needs to pursue, it is rather the side where we see additional warming that concerns us most. Now, the uncertainty there is not necessarily something that we will be able to avoid or reduce immediately, but that doesn't mean that we can't take it into account and prepare for it. And how can policy prepare for it? Well, policy can, or policy and decision makers can prepare for it and can take it into account by seeing net zero only as one step on the way towards a longer-term stable or longer-term response to the climate change challenge, and really prepare for a world where we actively are able to remove carbon dioxide from the atmosphere. I think that is, of course, the long game. First things first, a key aspect in reducing the risks that are implied by global warming and the zero emission commitment, or the potential zero emission commitment, is, of course, to reach net zero, or to stop adding CO2 to the atmosphere as soon as possible and keep those cumulative emissions until then to as low levels as possible.
Thank you, Joeri. Wonderful. I'm going to bring in Tessa now. So, as I said in my little preamble at the start, I thought I knew about zero emission commitment before I had that cup of coffee with Joanna Haigh, and it quickly turned out that I didn't. And also it turned out that it was a lot more complicated than I had first imagined. Given that it's complex, but important, how are we going to explain it best to policymakers who might not necessarily have scientific expertise? How do we do that?
Well, actually, I think Sofia's and hello, everyone. I mean, I'm really delighted to be part of this discussion. Thank you to Frontiers for the invitation to join you, and to Sofia for the really clear presentation. And I was just about to quote Sofia, actually, and thinking about how best to encapsulate, I think, some of the findings of this research. And that was really, I think, Sofia, you said that reaching net zero emissions doesn't mean a stable climate, whether that's still the possibility of increased warming or increased cooling. And I think that uncertainty, because the risks are obviously much more considerable if there is up to 0.3 degrees of additional warming even after we reach net zero. I think what that reinforces for policymakers, which to be completely honest, given the amount of uncertainty that's built into so many of the risks associated with climate change, I think what we have to insist on is that policymakers abide by the precautionary principle, which is a principle that's existed under international law and in international policy for decades, and basically means that where there is uncertainty, if the threat is great, then that shouldn't be taken as a reason not to take precautionary action. And I think that this research really underlines the importance of that way of thinking, and indeed that principle in informing policy making. So I think it's not an entirely new dynamic, I think, for policymakers to keep in mind.
Do you think many policymakers are even aware of the concept of the zero emission commitment?
I don't. I mean, I think that my experience is, in short, no. There is always a remarkably, I think, superficial engagement, from the perspective of people like us who think about these issues day in, day out, with the science underlying all of the policies and implications of climate change that we discussed. So I imagine this would be new to most people.
Yeah. So good for us to discuss it here, of course. I mean, given that the first step towards the zero emission commitment is zero emissions, what are the sort of regulatory frameworks and government policies that are needed to overcome the practical challenges just to get to that point?
Well, I think that's the discussion that, we've all been having for many years now, given that net zero, I mean, obviously after the endorsement of the Paris Agreement in 2015, that's emerged as the sort of collective North Star in policy making, and now a net zero policy commitment covers, I think, most countries in the world. I think there's generally an understanding, as Joeri was saying, that means that we've got to reduce carbon emissions. Ultimately, that's the bottom line. And I will say that one of the good things that came out of COP28 in December is, I think, finally connecting that understanding with the role of fossil fuels. We had for the first time the language of fossil fuels appear in a COP decision text, and an understanding that we need to transition away from fossil fuels. And ultimately, it's as simple as that. I mean, obviously, in terms of actually operationalizing that and transitioning our economies and our industries away from fossil fuels, that's going to require a whole host of different policies and practices. But I think, it is as simple as ensuring that we eliminate fossil fuels as quickly as possible from our energy systems and from our economies.
Thank you, Tessa. Charlie, to bring you in, you'll be aware, of course, that 2023 was the hottest year on our record by some margin compared to others, and a likelihood that this year will be equally, if not warmer, than that last year. I think it's provoking some people, some scientists, to predict a sort of runaway warming of our planet. Is that likely? And how is the notion of the zero emission commitment countering that type of idea?
Yeah, it's a great question. And yes, again, thanks everybody for this really interesting discussion. I think it's too soon to say, how out of, whether this, this incredibly hot year we've all just experienced is going to be followed by, an additional, whether it really represents a step change beyond just the, the proportionality of warming to, to our cumulative carbon dioxide emissions versus, if it's just one extreme year, and we'll see, things revert back to the trend, the longer term trend that we've seen. But I think one of the things that you do see from this is, the enormous, disruptions to ecosystems that are happening. Particular things like the fires in Canada over the summer is exactly the kind of thing that, we don't have a good ability to include in our coupled climate and carbon cycle models. And these are the kinds of effects that we, identify in the article as being, real uncertainties about the sign of the zero emissions commitment. If these kinds of large scale fires that we saw last year in Canada, if those become regular feature because of those the legacies and the lags of the ecosystems to the warming, can continue long after the warming has stabilized. Those are the kinds of things that could be contributing to a more positive zero emissions commitment and prolonged warming. And so I think these extreme years that we're seeing and the legacy of responses to ecosystems and as well to impacts around the world in response to these extreme years like last year are what we need to really focus on in order to reduce our uncertainty and understand how these abrupt changes that we start to see, whether or not those how those lead to longer term legacies.
Thank you. I mean, I guess the way to quantify predicting our future has to lie with models, one way or another, to do that. How good are our models and they're needed for that issue. Are they up to the challenge of doing what we need them to do?
Yeah, I mean, I think the difficulty of a metric like the zero emissions commitment is that it's not, it's not just the physical climate system, it's the coupling between the physical climate system and the ecosystems, both on land and the ocean. And so that's an extremely difficult problem, right? And it's, in particular, the representation of ecology in these models is not as strong, say, as the representation of the physical climate system. For a long time, the legacy of development of physical climate models versus quantitative, ecosystem models is, the ecology part of it is not as well developed. And I think that's one of the key things that we need to better focus on, particularly because these legacies in the system, a lot of them are driven by ecology, which is, not always been thought of as a predictive science the way, weather prediction, which then gave rise to climate modeling, has been. And so, it requires a very deep assessment of the uncertainties and understanding, and yeah. So we're building them. They're getting better, and they tell us this information that we have, and it's useful information, but it could always be better.
Thank you. Ben, on this issue, really, so surface warming is going to stabilize quite quickly after net zero emissions, but sea level rise and ocean acidification that continues potentially for centuries due to committed deep sea warming and ocean acidification, etc. How is this sort of disconnect between stabilized warming and continued other effects going to be affecting adaptation measures and climate resilience?
Well, I think we have this idea of net zero being a specific point in time, but it's really just one mile marker along the trajectory of decarbonisation. And in the real world, hopefully we'll reduce emissions, and then as soon as we do so, we'll see different effects emerge on different timescales, and we'll learn a lot. The moment we start reducing emissions, we will see how different elements of the Earth system are responding to those emissions coming down. And this question of zero emissions, we'll have a much better idea as soon as we start reducing emissions and we see what the Earth system does in response. And it's the same for sea level and ocean acidification. There's different processes which influence this, and they will emerge on different timescales. And we are the models which tell us about sea level rise in particular remain in the on the cutting edge, really, of what we can do with our system models. Only a few system models have interactive ice sheets, which tell us about the potential timescales and melting rates and their sensitivity to both warming to date and any additional warming which you would experience. But the uncertainties are quite big, and so we're going to have to live with those uncertainties in the in sea level projections potentially for centuries to come. And that part of the equation it's going to be a long time before the uncertainties get reduced. Other parts of the system, we might learn something quite quickly as soon as emissions start to come down.
I'm interested in the other disconnects as well. I mean, we talk about global climate stabilization, but does that mean stabilizing the weather systems on our planet? Will they remain the same?
I don't think we should expect the weather systems to stay the same. I mean, global surface temperature, even if ZEC is zero, so the discussion, this paper focuses on this global mean temperature response after zero emissions. But a zero global mean temperature change can hide evolving patterns of warming in the ocean as the deep ocean temperatures begin to warm, equilibrate, and then you get transfer in the ocean. And that could result in weather systems and weather patterns which continue to evolve over time as the system adjusts to a new equilibrium state. And in order to understand what that looks like, we need to build better models, clearly, but also we have to acknowledge that different models currently respond in quite different ways, and to post net zero emission conditions. In some models, ocean overturning circulation slows down, and these can have effects which emerge even a century after net zero has been achieved. So yeah, again, there is some fundamental uncertainty there that means that climate change, even in an optimistic scenario, may be with us for centuries to come, and will continue to change.
So Joeri, climate scientists are really good at acronyms. So the ZEC is the Zero Emission Commitment, and the TCRE is the Transient Climate Response to Cumulative Emissions. In combination, they provide a sort of means by which we can estimate carbon budgets consistent with temperature limits. Do you believe the carbon budget framework adequately captures the uncertainties relevant to guiding our pathways, emissions pathways?
Yeah, it's a good question. I mean, the carbon budget framework, in one sentence, is the fact that we have a total budget of CO2 that can't be exceeded if we want to limit warming below a certain temperature level. So the total amount of carbon that we can ever emit is limited. I think that is a very strong and powerful framework, first order framework. And for all the challenges that we are dealing with currently, it's a very good framework, I think. And to be sure, the challenges we are dealing with now is that our emissions are still going up globally. They have slowed down. The annual emissions, the increase has slowed down, but they're not going down yet. And to reach net zero, they need to go down quite steeply from the more than 40 billion tons of CO2 that we are emitting in the atmosphere. Now, where the carbon budget concept and the framework and the interactions between the zero emission commitment and the kind of the linear relationship between the total amount of CO2 and global warming might not be the perfect tool anymore. That is, if we are in a world where we have to start caring about the second order effects. And those second order effects we will see if we start to come close to zero. And so I think until then, this budget concept is still very valid. It has actually been proven to be also quite robust for projecting what needs to be done if we might be missing a target and we try to return. Also there, it's a first order approximation, but in order to communicate between very complex scientific understanding and systems and with policymakers, and to make that translation, I think it's a very powerful tool. So but that doesn't mean that the scientific community can't start to think about how we can more accurately use Earth system information at a time when we would have already reduced our global emissions by 90% or so, ideally over the coming decades.
Thank you. Tessa, on policy work, so your policy outlook paper highlighted the tension over the language regarding fossil fuel phase out in the COP28 negotiations, for example. How can clearer and more universally accepted terms and commitments be established to facilitate the rapid transition from fossil fuels?
That's a great question. And I think that the hugely contentious nature of the language around, fossil fuel phase out at COP28, which ultimately resulted in fairly weak language around transition that was heavily caveated at the national level, I think reinforces the importance of these conversations actually taking place at the national level, because reaching international consensus on these concepts and exactly how to express them is just so fraught. And I think the closer we get to addressing the root cause of the problem, the more entrenched I think those countries and constituencies that benefit from the current system are likely to fight back. And I think we saw some of that emerging at COP28 with a sort of contingent of countries who are heavily invested in fossil fuel production, for example, really refusing to compromise, and given it's a consensus process at the UN climate summits, it just makes it very difficult. So I agree with Joeri that the concept of a carbon budget is one, and not to make this discussion too UK centric, I appreciate a number of us are in the UK, but that's been translated into national policy making in the UK, I think, to great effect in the way that there is real accountability for 5 or 6 yearly carbon budgets for the UK government at the national level. And that's obviously a translation of the global carbon budget into what policymakers consider to be appropriate at the national level. So I think if there's a way of reinforcing some level of certainty around what the global carbon budget is, and then enabling national policymakers to translate that into a national carbon budget, which, in my view, should then be adapted to reflect principles of equity. So countries like the UK, moving faster and ultimately having less of that access to that carbon budget than other countries for various reasons. Then I think that that's a really strong basis on which to continue policy making.
And I guess there's initiatives like Beyond Oil and Gas Alliance, and the call for fossil fuel non-proliferation treaty. Are those organisations vital, important for this transition?
Yeah, they are, right? And I think, the Beyond Oil and Gas Alliance, I think, is a particularly powerful initiative because it is a multilateral initiative. It's it's a diplomatic club, basically, of countries that have decided to end oil and gas production or set an end date for oil and gas production, and have decided to end new oil and gas licensing. That's very useful insofar as, as I mentioned earlier, it spotlights fossil fuels as needing phasing out. Whereas I think just discussing emissions reductions can sometimes avoid the root of the problem, which is that need to transition away from oil, gas, and coal. And I think, it's exactly those kinds of initiatives that are helping to build momentum towards the transition away from fossil fuels that are desperately needed. And it's great to see them starting to get off the ground.
Thank you. Okay, Charlie, in the article, as Sofia explained really nicely, 26 levers of global temperature change after net zero. That's a lot of complexity. Going back to what we sort of talked about before, how confident are we that we're able to predict the trajectory of global temperatures post net zero? And what are the major sources of uncertainty in all of this?
Yeah, so the part that I focused on in the article was the land ecosystem, the land carbon cycle response, and the various processes, which include things like permafrost thaw and the legacies of permafrost thaw in terms of carbon emissions, and as well as wildfire and dieback of forest in tropical ecosystems, in boreal ecosystems around the world. What all those things have in common is the legacy of the ecosystems to prior climate change, prior disturbance, prior land use change. And these are the things that, because we are focused on, what are the remaining uncertainties, these are the things that are still the most highly uncertain, is these slow legacy responses to things that had happened, decades before. Because, the essence of the idea that, that the ZEC is small is, as Sofia explained, is this trade-off between the sort of declining CO2 uptake on land and the ocean and the declining heat uptake. And so it's really about the rate of that decline, and the relative rate of those declines. And because, the relative rate of those declines is, a function of these timescales and legacy responses, those are the key things that we need to focus on. And yeah, again, because we're focused on the article on the biggest remaining uncertainties, those aspects of the system are quite uncertain, and that's why if you look at the current set of climate models, they give you, they give us this uncertainty of about plus or minus a third of a degree Celsius. That uncertainty that's represented in the models is then reflected in the the widespread of the ensembles of these coupled carbon climate models. And so again, these models are useful in that they tell us, something that we can use to influence our policy. But again, in order to improve them, in order to narrow that uncertainty, that's what we need to focus on, or better understanding these legacies of the carbon cycle to the response.
Yeah, thank you. Ben, on this issue on uncertainty, okay, so money no object, geographical location no object. Where should we best target research that will most reduce uncertainty on this issue? Would you say? And you might talk about your own research or anyone else's. Sure.
Yeah, that's a big question. So I think, well, let's say, firstly, one thing which was good about this article, and it is rare, is it didn't just talk about what's in the models, it also talked about what's not. And even though it's difficult, attempted to sort of like order magnitude, assess what the magnitude of those processes which are not in the models is. And so that's a useful exercise in informing the question that you're asking is, okay, well, that's how do we triage how to include processes in the models which are not currently represented. And so that exercise is a direct, useful takeaway from this article. And aside from that, we need to think about how to deploy the resources that we have. I know you said that money was no object, but as we move into sort of another big round of IPCC assessments, it's useful to think about what resources we have on the table and what experiments to do to better get a handle on these questions moving forward. So involved in that is how we use the different types of models we have on the table. We have some complex models like several of us work on here, like Charlie, and we have lots of different sort of simple models which allow us to sort of more look in a more formal statistical sense at all of the uncertainties in the problem. And so what we're trying to do now is how to use those two different types of model in parallel, noting that neither one is perfect. The complex models, we can never run them enough times to get a full grasp on the uncertainty, and the simple models, we know there's a bunch of stuff missing. And so we need to sort of smash these things together in a way that gives us a better understanding of what's happening moving forward. And then together with that, you've already raised the issue of like 2023 and how that that's taken some climate scientists by surprise. That's the other element of this. That how can we get more efficient at more rapidly incorporating observations which we have of the climate system back into the models to influence how they're calibrated and what processes are missing. And so with that in mind, then this question of ZEC, the zero emissions commitment, is one of a few which really matter in terms of framing policy. Another one is what's going to happen as the aerosol emissions come down. I think that's really been highlighted as a big uncertainty, which we need to do better really rapidly. And then how do we incorporate observations, for example, from satellite time series, which are now becoming mature enough to actually be used as ways to either to determine between good models and bad models. So there's a lot of things which are happening simultaneously, which we need to sort of incorporate.
Thank you. I was rather hoping you'd say deep field Antarctic glaciology research is really needed, but then there was another matter we can have a conversation about. Final question to Sofia, and thanks again, Sofia, for organising us and for putting this paper together. Is net zero enough? Or should we be aiming for negative emissions? And in that case, how do we do it?
Yeah, good question. And I'm glad that you phrased it like that and not is net zero worth it, because it absolutely is. Yeah, well, I think this paper has highlighted that perhaps net zero won't be enough, although it is absolutely required. And I guess that in order to answer that question, we need to be able to look into the future a bit and know what level of warming we've reached at the point that we're at net zero. And if it's quite high, then absolutely we're going to want to bring that temperature down. And the way to do that is through net negative emissions. So, yeah, I think it's a bit of a case of, the more that we know, the more that we notice our uncertainties, and the more that tells us that we need to keep global temperatures as low as we possibly can in the first place. And if we can't do that, then to bring them down as much as possible afterwards.
Thank you, Sophia. It's good to know we've got an awful lot of questions coming from Q&A. And so with that, I'm going to hand back to Gilbert. Thank you, Sophia. Thank you, Tessa, Joeri, Charlie and Ben. We're going to hand back to Gilbert. He's going to take us through the audience Q&A from here. Thank you ever so much.
Thank you, Martin. It was a really great discussion for charting a real path forward. Yeah, we've had loads of questions coming in thick and fast, and a lot of them are elaborating on the points that all of you mentioned. So I've just picked a couple out, and hopefully this will add a little bit more depth to this discussion. So let me just get started. And I think the first question I'd like to discuss is actually perhaps one of the most challenging ones. And it's on the practical challenges of reaching and sustaining net zero emissions. And as moderator, Martin, I'd love to kind of direct this one to you, if I may. So, Tessa mentioned, and we know the outcome of COP28 about the importance of vocabulary when we talk about the fossil fuel industry, phasing out, phasing down, transition away. So the fossil fuel industry and its enablers remain a major obstacle to achieving net zero, and this we all know. What can academics do to minimize the fossil fuel industry's influence on international policy and politics?
That is a terrific question. Thank you, and not an easy one. But then again, well, maybe it is an easy one. There are when we talk about the fossil fuel industry, it's a wide variety of different types of companies, different types of behavior, different appreciations of the climate problem. So it's easy to sort of lump them all together as the fossil fuel industry, but actually it's actually quite diverse. There are some people who think we should simply not have anything to do with the fossil fuel industry and put them all into one place. I don't know what other members of the panel are like that, but I'm not in that position for two reasons. Firstly, actually, there are some companies that are more enlightened than others. And it is, I think, appropriate to work with companies that are serious about the transition to net zero, and not work with the companies that clearly, through their records and through what they say, actually they're not at all. The second reason I'm interested in continuing dialogue with this industry is that they've got tremendous expertise built in terms of putting very large bits of kit in difficult places, raising large amounts of income, investing in that, making it work financially, turning into a profit, providing energy to our global system. That's exactly what we need to advance renewable energy at pace and at scale. And so just to say we're not going to work at all with the fossil fuel industry stops us working with the very companies that are good at doing what we need. Now, there will be some fossil fuel companies that you just know won't do it because they obfuscate and they lobby against climate actions, and so don't work with those. But there will be some, and hopefully more into the future, that maybe do get it better. And it's for those companies, and it's for each of us to work this out. It'll be for those companies that we should maintain our focus, I think.
Thank you very much, Martin. Tessa, I don't know whether you have anything you'd like to add to that.
No, I appreciate Martin's perspective on this. I think it's right that there is diversity in the fossil fuel industry. I do think, though, that it's important to bear in mind the sort of the gulf at the moment between the sort of rhetoric that we're often hearing from the industry in terms of the role that they'll play in the transition and where their capital expenditure is going and their investments are going. And I think the International Energy Agency's one of their recent reports made it clear that fossil fuel companies are responsible for only 1% of investments globally in renewable energy generation. So overwhelmingly, it's not the fossil fuel industry that's currently driving the transition. And I think that for a lot of us, the last year or so, when the industry's been making record profits, has been a real test of the intention of that industry to play a part in the transition. And what we've seen overwhelmingly is that they are paying out their shareholders and paying off debt, and they're not investing or diversifying their portfolios. In fact, we've seen rolling back of some of the commitments to expand renewable energy production from some of the carbon majors. So I certainly appreciate, and we work with the oil and gas workforce in the UK, because they absolutely do have the skills that could be repurposed for, certainly if you're looking at offshore oil and gas, into offshore wind, for example. And I think it's very important to think about how to harness the expertise within the workforce. But I do think that, it's really important to be quite discerning about which companies are acting in good faith and which ones are trying to take advantage of the reputational boost they get from talking about being part of the transition when their investments and, where they're putting their money belies that.
Thank you very much, Tessa. I guess that's a contentious topic that we can talk about for a very long time. But I would like to now pivot the discussion, and maybe let's look at the modeling and the work that Sofia was presenting. And we actually have a question from one of the co-authors that came in, Joeri Rogelj. Yeah, I guess this will be open for takers, but I'll read it out. And it's about the evolution of the Earth system processes after reaching net zero emissions. So the question is, as you said, land vegetation responses are highly uncertain, and most Earth system models don't couple it fully. Of the 5 with fire in the recent IPC carbon cycle chapter, only 1 or 2 also have interactive vegetation. To understand what happens in response to extremes, for example, like some of the ones we see, we need to know about these interactions. How can we entice modelers to fully couple it, even though it is difficult and may go wrong? Is there a way we simulate the future models that can be still appropriate?
I mean, we're, the community is definitely doing this, right? We're building models that do a better job. Each successive generation of Earth system models, includes more processes than the prior ones. If the table that Gabrielle is describing, if that equivalent table was there in the prior IPCC report, and now I can't remember whether or not it was, it would have a lot more sort of missing processes than the one for the 6th assessment report. And I think we expect the 7th assessment report to, when it comes to have more models with more processes. But it's slow, and I think that so much of the focus right now, and historically, has been on increasing the resolution of the atmospheric models and and these physical processes, and I think a somewhat smaller focus has been on representing the fidelity of ecosystem models in the land and the ocean, in these coupled Earth system models. And so it takes to sort of the point that Ben was making before. It takes takes some prioritization, and it takes resources, and it takes better data and observations. We can only build these very complex models if we have very good observations from satellites and from field observations, and et cetera. I mean, we need all these things together, right? So it's not there's no single solution to every that's going to make our models great. It's a whole large set of interacting processes and a whole large set of interacting institutions and observational resources and modeling resources. So all these things are needed together, and it just takes time and effort and people and resources.
Thank you very much, Charlie. That was quite a challenging question that your co-author also shared. I'd like to maybe kind of pivot this back now, thinking about monitoring and measurements. So we have a question here from someone called Cheng-Ji Zhu, and it's on the research priorities for reducing zero emissions commitment uncertainties. So the question is, I appreciate the talk on the uncertainties in the projection of future climate change. To narrow down the uncertainty, we need to have better climate models. There are multiple studies showing that the current climate model simulations of climate trends are much warmer than independent satellite observations, which have global coverage. How can the climate model community take steps to improve the climate model simulations to have better agreement with these recorded observations? Would anyone like to take that? I don't know, Ben, if you would like to tackle it.
Yeah, sure. I mean, it's so I mean, this question of whether the current models are too warm or not is a constantly moving. You know, it's constantly changing. You know, we get more observations all the time. Last year was very hot. We still haven't, you know, the papers which disentangle how to interpret the models we have given last year's observations haven't come out yet. So that would be my first point, is that, you know, this is the conclusion which the next assessment will have on current models will be different to this one. And also it's there's lots of different lines of evidence here. It's not, there's no single axis through which a model can be better or worse, you know, because there's a climate model simulates thousands of different processes in different parts of the Earth system. One way to assess it is through global mean temperature, but also you can look at any aspects of local climatology or the land surface or the carbon cycling or anything else. And so we need to then process that information to say what they mean. How can we build better? So the question was framed as we need to build better climate models to have a better, or to reduce our uncertainty. I mean, I would say it's not quite as simple as that. We need to identify our uncertainty. You know, there's no firstly, there's no single way to assess when a model is getting better or worse. You know, you have to come at this from lots of different directions at the same time. But also you have to be satisfied that you're sampling the degrees of freedom which you have in that model to sample processes. We need to be confident that our ensembles and our sampling strategy are exploring the degrees of freedom which we have in order to be confident that we're not missing a potential worst case scenario. Yeah.
Thank you very much. Would anyone else like to speak to that, or shall I can move on to our next question? Yeah. Oh, okay. Joeri, would you like to kick us off?
Maybe I also want to actually link this back to what Ben mentioned earlier. The most complex models that we have are extremely expensive to run. We will have one calibration of them, and we don't expect that calibration to be perfectly in the center of the distribution. That means that we can't just rely on these most complex models to give us the best estimate, central estimate of our projections. Instead, we can use this kind of ecosystem of models with the most complex, the most advanced ones, and then simpler ones that can be run thousands, if not millions of times, and that can capture all the uncertainties, including then have a median response that is really also consistent with the kind of median estimate of what happened in the observations. And it's really this interplay between these different levels of complexity of modeling that needs to be further developed. We saw a first really good indication of this actually in the last IPCC assessment report, where the most complex models, the temperature projections of those, were not taken as the standard by which future warming will be judged. They were taken as information, as insights that are then integrated in our assessment of what future warming will be. And it is this kind of integration of these different lines of evidence that is really very important and will become ever more important in the future.
Thank you very much. I know, Martin, you wanted to
thanks, Gilbert. Briefly, and just to sort of exemplify this issue in Antarctica last year, the sea ice in Antarctica was reduced over winter by an area about 10 times the size of the United Kingdom. that should have been covered by ice on the ocean, and it wasn't. And it was remarkable how little it was and how far away from previous years that ever was. It's been happening in the Arctic for some time, since the 1970s, that we've been revealing that Arctic sea ice has been lost. Up until 2017, that really wasn't happening in the Antarctic, but most climate models kind of had that, the Antarctic sea ice behaving kind of like the Arctic. And we always wondered why that was. Maybe the Arctic, the models are just overheating, maybe they're doing this. Actually, since 2017, the sea ice in Antarctica has been getting less and less. And this year, remarkably so. So it just might be the models are right after all. And there's a lot of sort of variability and uncertainty in the Southern Ocean. But actually, over the long term, they've probably got that right.
Well, that's actually leads to a great follow-up question about the predictability of these models. And it's good to see, empirically, you managed to get them pretty accurate. So I actually have a question that comes in from one of the Frontier's chief editors. So that's Professor Michael Heinrich. So a warm welcome to you and thank you for joining us. So this question is to Sofia, and you have partly answered this, but I think it's just nice to see the research direction you're going to go into. So environmental systems are always fluctuating, and there is a high level of uncertainty, a point that you highlighted very eloquently. So Sofia, what do you think is needed to increase the predictability of these models, or the next stages, I would say?
Thank you for the question. I guess this is the part of the paper that I didn't really go through in the talk because there's quite a lot of information that comes with it. But yeah, one of the main things that we tried to do was really articulate what it meant for research, taking each of these processes and trying to improve the predictability we have about them. So I would, perhaps inconveniently refer you to our paper where we have that full list of the 26 processes and suggestions for research questions, and then beyond that, suggestions for actual modelling exercises that either are waiting to be done in the sort of near future or that we need to make some effort to make happen. And we've really tried to prioritize those via like a few different dimensions. So whether we may already have like the correct materials to be running some of these experiments separately from our most complex models. So it might be that we have a model that just runs something about land carbon or just runs something about CO2 exchange between the ocean and the atmosphere or whatever it is, and that trying to reduce our uncertainty in a certain measure that can then be fed into the more like coupled comprehensive systems. And so we've made an assessment based on that, of what's available at the moment, but also what the kind of big modelling exercises are that are coming up in the future that we know about, and also the big reporting exercises. So the future IPCC reports and also the coupled model intercomparison projects, and thinking about how this question can be integrated into those exercises that we know are going to happen anyway. And then the zero emission commitment model intercomparison project, which has been run separately and underlie a lot of the kind of question that led to this paper coming about in the first place. There's going to be a second iteration of that as well. So certainly there are things that are going to be put into practice going forward. And if you're interested in what those specific questions are, if, for example, you're interested in performing some of those pieces of research, then that would be a great resource for you.
Wonderful, Sofia. Thank you very much for sharing that. I'd like to follow this up with a question. We're all familiar with the 9 planetary boundaries. So this will obviously have an impact on how we understand our interaction with our natural world. And I just want to paraphrase this question somewhat because I think it's kind of missing a point. So this is a question from someone called Leonard Niamtu: the implications of zero emissions commitment uncertainties for climate policy. Should the planetary boundary thresholds have them adjusted if we're considering the possibilities of what would follow a net zero world? That's an open question if anyone would like to take it. Joeri, I see your hand up. Yep. Short
answer, no. Because the planetary boundary, well, as currently defined, there are 9 of them, looking at different parts of our planetary system, and one of those boundaries is on climate change and on, for example, on CO2 concentrations and climate forcing. They are kind of on the interface, and they strike a balance between scientific evidence, scientific understanding, and ultimately value judgment of what we consider safe, what we considered acceptable, and what thresholds should not be exceeded. A similar question has been answered by countries under the Paris Agreement, and they were asked what is a safe level of warming, or what is an acceptable, I don't think they would call it safe, level of warming. And well, they translated this in that the aim should be to keep warming well below 2 degrees while pursuing to limit it to 1.5. So that's a similar kind of boundary. Well, that boundary should not change with this information. The implications of what we need to do to stay within that boundary or to stay within the Paris Agreement temperature goal, yes, that should take into account the information of this research. And well, I already highlighted some of those implications before. There are implications for how large the remaining carbon budget would be. There are implications for what we do after net zero. There are implications for how we prepare today for that later eventuality.
Great. Yeah, thank you very much, Joeri. That's super clear. Anyone else would like to share on that? We're all good. Okay, we're running out of time, but I'd like to just bring in Tessa in again to perhaps speak a little bit more about climate policy and elaborate what you were saying before. So this a question from someone called Emilia Delgado, and it's the implications of zero emissions commitment uncertainties for climate policy. So Emilia, thanks you for reminding us of the precautionary principle. It should be widely known. However, from her experience, environmental related risks seem to be categorized in some special category and they're not regarded in the same way and they're discarded. So any advice on how we can make it more visible, make these more visible to the decision makers?
It's a great question. And I think it's a frustration that lots of us who work on climate change policy and who also understand how long the precautionary principle has been around in sort of international law and policy making. It's frustrating that it's yet to translate, I think, in any persuasive way into domestic policy making, although there are some exceptions to that, where environmental impact assessments, for example, have incorporated the precautionary principle when thinking about the approval of big new infrastructure projects. But I mean, honestly, I think that just the fact that, as we've been discussing, the last year was warmer than people had predicted, that we are sort of starting to see how the uncertainties that we're grappling with can often mean that risks manifest sooner than we expected and not later. I actually think that the evidence that people are experiencing directly, physically, seeing around us, and policymakers aren't immune from that. And, we know just in the last year, every continent, more or less, has experienced, I think, some manner of extreme weather event or the implications of our changing climate in a way that's, affected their local communities. So basically what I'm saying is I think the case is easier and easier to make with every passing day. And I think it, intuitively is more and more appealing as we see more evidence of our failure to take account of those risks and act in a precautionary way. So hopefully that, that the external context in some ways is going to make that task easier.
Thank you, Tessa. It sounds like a complete double-edged sword. But yeah, I think the fact and the reality that we're all facing it should usher in more climate action on policy fronts. So I'd like to now end this with something a little bit more positive. And after reading Michael Mann's editorial about how technology and the know-how actually we're there, but the actual obstacle is policy really. But then we also are thinking about capacity building for the next generation, right? Like we know that we're going to be passing this on. And this is an open question for anyone who'd like to share. What do you hope school teachers are doing to help the next generation to understand the latest climate change research and the roles they can play in mitigation and adaptation? Is your research relevant to climate change education in schools? And I'm happy, first person who'd like to put their hand up can take it.
I imagine that all of us care about the next generation and the leaders of tomorrow, that they're at school today, right? And the better we can equip young people with the determination and with the knowledge and the skills that they're going to need for the next 40 years, which is the net zero transition period, the better it will be. And so that we have an obligation to talk to school kids about this and to alert them to it. Now, something like the zero emission commitment, and it's quite challenging. You don't have to start at that position, you know, that's kind of quite advanced level stuff. But the great thing about climate research is that it's easy to engage a broad audience with it because it's our planet, right? We need to fall back in love with nature and with the planet. And in my experience, and I go to many schools and secondary schools in the UK and all around the country, the level of engagement is spectacular. The kids really do want to understand and know about this. And as I say, it's our obligation, especially those of us who work in research institutions and in universities, to reach out to those, because in 10 years' time and then afterwards, many of those will be working as we do now in this area. We must advance things, you know, we must pass on our knowledge for the next generation to build on it as rapidly as possible. Thank you.
Thank you. Joeri, who would like to share?
Just adding to this, I also wanted to highlight that the resources that are already available, and actually Sofia led an additional paper in Frontiers for Young Minds on this topic, for example, as an explainer to school children, which might already be a starting point. There are also lots of initiatives, including by research projects to translate Earth system science for mostly primary and secondary school children. So there are really targeted resources available. And I cannot agree more with Martin that we need to equip the next generation. At the same time, we should not abdicate responsibility because the decisions that need to be taken today, and the actions that are actually required for a safe planet are the actions that happen in the next 5 to 10 years. And that's when they are still in school.
Thank you very much, Joeri. That's really useful. Any other final thoughts from anyone? Maybe Sofia, how did you find the art? Oh, Ben, sorry, I just missed you.
Yeah, just very briefly. Questions like this tend to make us focus on uncertainties because that's the way the question's framed. And they tend to underplay how much we are kind of confident about. And in this particular question, we are confident that, as Joeri said before, the first order effect, like every ton of carbon you put into the atmosphere, you get a certain amount of warming. Broadly, that remains true. And we're talking about like the second order details on top of that. And so I think the first thing to do is like communicate that a lot of climate science can be explained, you know, very simply, very clearly, and then also be very clear about you know, where scientists do disagree on like mitigation strategy and what we should do about it and how we should structure technology and society and everything else. We have a clear, open discussion about why different people have different opinions. And so, yeah, I think there's a job for climate scientists to sort of, you know, say what they know and why they disagree on what they don't. And yeah.
Brilliant. Thank you very much, Ben. I'm just cautious now that we've just reached the end. It's 20 past, so we can, you know, Charlie, if you have anything to share, you can also share in your closing remarks. But I'd like to say thank you to our audience, and I'm really sorry we just scratched the surface with the plethora of questions that came in. It's been an absolute pleasure to see how engaged everyone's been. But I'd like to now close this and now just follow up with some closing remarks, and I'd love to offer the opportunity to Joeri, perhaps looking at the critical next steps for this research as you see it.
Knowing the material, listening to the conversation that we had today, I think the critical next steps is really first and foremost to translate it to policy and to translate the insights and make sure that the consequences are understood. I mean, this evidence should incite action, not necessarily surrender. But it is also clear that additional warming does not mean unstoppable warming, not at all. Net zero still becomes even more important as a milestone, but it's not the end point of how society responds to the climate change challenge. And there is uncertainty about how much warming we will get, which additional impacts there could be, the damages and the challenges, but this uncertainty doesn't mean we cannot act. And from a precautionary principle, actually, a precautionary approach allows us to take this uncertainty into account and hedge against these risks. And so the consequences there are clear. Emission cuts over the next years and decades become ever more important in order to limit the peak warming as low as possible. And besides those reductions, also investing in long-term removal of CO2 from the atmosphere as a key protective measure against additional warming becomes important. What that means for research, what I heard from today's conversation is an important focus on better understanding the different factors that influence the zero emission commitment that have now been identified by this study. And this better understanding can be built through modeling and observations. And we should particularly look at those factors that are currently only identified as speculative, that are not in the models. And we heard, for example, legacy effects of warming on ecosystems and ecology. But we equally heard not just the challenges of building a model, but also the challenges with the observational coverage and the observational evidence of the systems that we try to model. If we have not observed them, it's really hard to build a strong model. Together, these steps will really ensure that society is better equipped to respond to the climate change challenges, and that we are of the climate change challenges, which we are and will be facing over the course of the coming decades, if not centuries.
Thank you very much, Joeri. We are very, very close to running out of time, so I'm going to give the panelists a challenge. If there is one word or phrase that you would like to share with our online audience as a take-home message, what would it be? Ladies first. Sofia, may I ask, how would you impart your knowledge?
Well, I think, the most important thing really is to echo what we've had a lot today, which is that this uncertainty in the Earth system does not translate into any ambiguity about the action we need to take. The message is still the same, and it has been for decades. We need to reach net zero, and we need to reach it as quickly as we can.
Crystal clear. Thank you. Over to you, Tessa.
Yeah, honestly, I don't have much to add to that. I think just the urgency of the imperative to get to net zero, given potentially the importance of getting to sort of net negative emissions, if it turns out that we fall on that side of the uncertainty spectrum. So I really just think that it underlines the importance of that really rapid and deep cut in emissions in the short term.
Thank you very much. Over to you, Ben.
Yeah, I think in addition to everything which has been said today, a great challenge is now to assess policies which claim to get us to net zero and really dig into the details of what's implied, especially on the negative emissions side. So it's a different discussion, but I think that's really important.
Fantastic. Charlie?
Yeah, just that the zero emissions commitment is, it's very closely related to this idea that warming's proportional to cumulative emissions, and that's the important model. The most important model is the one we have in our minds, and if all you really need to understand is warming's proportional to cumulative emissions, and we just need, if we want to stabilize warming, we need to get to net zero.
Absolutely. Thank you very much. And Martin?
Yeah, the co-benefits of decarbonising are really important, right? The things that we care about on our planet will be protected with rapid, deep decarbonisation. If we don't do that, those things that we care about, the polar regions, oceans and things, our climate will be devastated. So the sooner we do this, the better.
Thank you very much, Martin. Thank you, everyone, to all our speakers and our expert contributors. Thank you, Sofia, Martin, Joeri, Ben, Charlie, and Tessa. And also, thank you to everyone who joined today. I really hope you enjoyed the session as much as I did hosting it. So a quick note, please do visit the Frontiers in Science website, do read the article that we've discussed today, and explore the hub of content. There's really, really great material that you can get your teeth into. As I mentioned, the conversation is still going on social media, so use the hashtag Frontiers Forum. And also I invite you to subscribe to the Frontiers in Science newsletter via the website. So for now, a big thank you. Thank you, our panelists, and have a lovely morning, afternoon, and evening. and catch you at our next forum. Thank you very much.